So turning to slide 49, we have the outline here again. So after all of these discussions of modeling ideas, we're now turning to focus on applications of latent transition analysis and also the new random intercept latent transition analysis. And we're going to do that in the context of 3 different data sets, and those data differ in terms of the number of time points, the sample sizes, the number of indicators per time point, and the number of classes. And at the end of this, we're going to discuss whether or not LTA is the right type of model, or are we fishing in the wrong pond. Just to remind you of the RI-LTA, take a look at slide 45 again. So at the bottom of this slide, if you look at the boxes and the circles at the bottom, we have the regular LTA. And if we include the top part as well, then we have the RI-LTA. So we have a random intercept factor that influences each item equally across time, but different items have different factor loadings. Now, as an aside, we could have had a slightly more general model by having a random intercept latent variable for each of the indicators per time point, influencing the indicators equally across time. So that would be 2 dimensions of integration in maximum likelihood terms. And it seems like for the data that I've looked at, that you don't need to go beyond this single random intercept factor, a single dimension. But you could, and it's, however, impractical when you get many more indicators. The number of dimensions increase beyond what you can handle easily by maximum likelihood. And Bayesian analysis in this mixture context can be quite tricky to carry out. Now, the first observation we make is on slide 50, the fact that the fit is typically much worse for regular LTA than RI-LTA. In the first paper, in the first version of the paper, we analyzed 4 different data sets: life satisfaction, mood, reading proficiency, and dating. In the second version, we only work with mood and dating. Here we will talk about reading as well, but we'll do a more thorough analysis of those data than we did in the first version of the paper. This life satisfaction example comes from a chapter contribution by Leinheine and Van der Poel in 2002 in the very nice applied latent class analysis book edited by Hagenars and McCutcheon. That reference is given on slide 4. So what you're looking at here then is the number of parameters, the log likelihood, and the BIC, the BIC, where BIC is scaled so that lower values are better. So BIC tries to measure how good the likelihood is, but giving a penalty for using many parameters. So you want a parsimonious and model that fits the data, or where the likelihood is high, so you're closer to the data. And in any case that you look at here, the BIC improves radically. It drops quite a lot, 30,745 to 30,637. And same for the mood data, 4150 to 4093, 4380, etc. Big drops. The log likelihood is also given. Now, you should notice then that what we have here is the difference in number of parameters in any case here is the number of indicators per time point. Here we have 1 indicator per time point. By the way, here's a type which should say j equals 2, 2 being the number of classes. Here we have 2 indicators per time point, so we have 2 parameter difference, 5 here, and 3 here. Now in terms of testing whether or not the aura LTA is necessary. That's a little difficult because we get into testing when the new model adds a variance component, the random intercept factor. So that's a tricky topic. You can work with mixtures of chi-square distributions, but it's not clear exactly how you would apply that to this situation. So I'm going to leave that aside. Nevertheless, we're going to note that, like here, there's a huge difference in the log likelihood here, which if you did the regular 2 times log likelihood difference test, it would be a very large number relative to only adding one parameter, that is a 1 degree of freedom test. It's going to be sufficient for us to look at BIC alone, given these large drops improvements in BIC. So let's take a look at our first data set then, which is the mood data. So this comes from an article by Eid and Langeheine, and it draws on data from a German multidimensional mood questionnaire. So here we have a rather low sample size of only around 500 observations, which is low in LTA settings. You really want a couple of thousand. And here the individuals are measured 4 time points, as I mentioned, and 3 weeks apart. We have 2 binary items based on ratings of momentary sadness and unhappiness. We're going to work with a stationary model, which means that we're going to assume that the transition probabilities are equal across time. That's a simplification of the model that quite often fits quite well and certainly simplifies the interpretations. So this comes from this article, 2003. And just repeating then again, the model fit here in terms of log likelihood and BIC, regular LTA, 7 parameters, and RILTA adds 2 parameters, 1 for each of the 2 indicators per time point, so the 2 factor loadings. And we see this substantial improvement in BIC. So then let's take a look at interpreting this model for both the regular LTA up here and the RILTA. And as we did with the dating example in the first early segment, I think it's segment number 2, we will start with interpreting the measurements. That is, looking at the measurement probability pattern to understand what the classes mean. So the column here are the classes, 2 classes. We're going to call them high mood and low mood. We have the indicators sad and unhappy, so they're binary. U equals 1 means that you're sad, U equals 0 means that you're not sad. Same for unhappy. And you see then that if you're in a low mood, you have a very high probability of endorsing the sadness item, of saying that you're sad. That is U equals 1. And you also have a high probability of saying that you're unhappy. If you're in the high mood class, if you classify as a high mood person, then you will have a much lower probability of saying that you're sad and unhappy. It's not 0, so it's not perfect measurement. You can think of this as a measurement error of sort, either by people carelessly answering or interpreting the sadness and unhappiness items slightly differently. Now, if you compare that to what we get from RILTA, you get a little bit of a different picture. You get less discrimination between the probabilities here, the high mood and low mood columns. That is, these probabilities are a little bit higher, less close to 0 than they were for the regular LTA. So in a sense, this measurement model gives an impression of the items measuring the mood much better than what they do down here. Now, that's not a reason for choosing a regular LTA, because if this is the true case of affairs, as the better model fit indicates, then this would be a distorted view of a wrong impression of good measurement. And then the second part of interpreting the LTA is looking at the transition probability estimates. So here we have, again, high mood, low mood, and the classes, the rows are also high mood, low mood. So for regular LTA, we have a fairly high probability of staying in a high mood from 1 week to 3 weeks later. Same for those who start in the low mood. They're very likely to stay in the low mood. Now with the RI-LTA, it's quite different. You have a higher off-diagonal probability, therefore a lower diagonal probability, and particularly so for those individuals who start in a low mood class. They're almost equally likely to stay in the low mood as they are to move to a high mood. And that's quite different. That second line is quite different from the second line for regular LTA. And it remains to be seen if that is a common type of outcome, but it is the case that it is quite likely that the RI-LTA lowers the diagonal elements of the transition matrix, as it does in this case. Now, if you expand the model, we looked at the top part before. If you expand the model from the standard LTA situation, be it regular LTA or RI-LTA, to including a mover-stayer latent class variable, a binary latent class variable, where we try to figure out if you can identify movers and stayers, where stayers are those who have probability 1 of staying in the same class and probability 0 of transitioning to other classes. So if you take a look at regular LTA here, and you're adding then one parameter, going from 7 to 8, that's the probability for being in the mover class or stayer class. And the BIC improves quite a lot, 4150 to 4123. So if you use the regular LTA, you would conclude that you should have a mover-stayer model, not just a standard LTA model. Now if you look at RI-LTA, it also adds one parameter, but BIC does not improve. In fact, it gets a little bit worse. So with RI-LTA, you would tend to stay with the RI-LTA standard model up here, which is still better in terms of BIC than the mover-stayer regular LTA here. So that's what I summarize in the first bullet at the bottom here. And there is perhaps a general feature here, that when you use this random intercept factor, that you have less of a need to add a mover-stayer component to your model, because the factor values, the factor scores for the random intercept factor, can to some extent capture stayers. For instance, if you have positive factor loadings, a high factor value in this case would tend to say that you are likely to answer in the sad and unhappy categories at all time points, remembering that the factor is really like a trait, or is a trait, that is something that is time invariant. So if you have a high positive factor score, that will tend to say that you're more like a stayer. So this is a continuous version of the binary mover-stayer model that you achieve by adding this random intercept factor.